Section 5.9 is the last one in Chapter 5. It's titled Operations with Complex Numbers. In this section we're going to do a variety of things. We're going to graph complex numbers, find absolute value, go over the 4 basic operations, how to add, subtract, multiply, divide complex numbers, as well as we'll look at powers of imaginary numbers. When graphing complex numbers, you have to graph complex numbers on a complex plane. It's not a real plane. Now, it looks like a real rectangular plane. Instead of an XY axis, we have a real axis, and we have an imaginary axis. Okay, so when I want to plot the point 4 minus 3i, it's kind of like plotting the ordered pair 4 comma negative 3. Not kind of like it is like plotting the ordered pair 4, negative 3. I go to 4 on the real axis, negative 3 on the imaginary axis, and put a point. It's 4 minus 3i. Okay. Like that, I can do all these numbers. 9 plus 3i goes to 9 on the real axis, 3i on the imaginary axis. There's 9 plus 3i. Negative 4i doesn't have a real number, so it doesn't go anywhere on the real axis. It just goes down 4i on the imaginary axis. Okay. The last one, negative 4 plus 7i, goes to negative 4 on the real, goes to 7i on the imaginary. There's negative 4 plus 7i. Now the reason why we would want to graph complex numbers in this course is that it leads us into our first operation that we're going to go over with complex numbers. That operation is finding the absolute value of complex numbers. We know that when we find the absolute value of a real number, it's just how far is that number from 0 on a number line. Well, since complex numbers have 2 components, they graph in 2 dimensions here, it's not going to be how far from 0 on a number line, but how far from 0, 0 on a coordinate axis. So negative 5 plus 3i plots right here. The absolute value is how far is that point from the origin. Now, the way I like to do these types of problems is construct triangles and use Pythagorean's theorem, which we should all know from geometry. If I come down and across, make a right triangle, the distance up is 3, the distance across here is 5, and so we can find the length of the hypotenuse by doing 3 squared plus 5 squared equals c squared. That's 9 plus 25 equals c squared. So c squared is 34. Therefore c is the square root of 34. That is our absolute value. Okay. Now the next example offers us a little bit simpler problem. Negative 4i plots right here. And what I want to know is how far is this number from the origin? Well, since it's actually on an axis, we can just count how many boxes we counted down. We counted down 4. So that's an easy one. Typically, points that you're going to have to find the absolute value are outside off the axes, and then you got to use probably Pythagorean's theorem to do it. Next, I'd like to look at operations with complex numbers. We'll begin with addition and subtraction. Now, when you do addition and subtraction, it's actually just adding and subtracting like terms. You don't have to know that the I is an imaginary number. You can kind of pretend that the I is just any other variable that you might encounter in a problem. And so when I add these together, I'm going to add the real numbers, and I'm going to add the imaginary numbers. Negative 3 plus 5 is 2. 2i plus 6i is 8i. And that is the end of that problem. Okay. Subtraction is pretty much as easy as addition is. I find my like terms. And so I begin here with the real part. 10 minus 10, that's actually 0. Those cancel out. Negative 3i minus negative, so the minus negative becomes plus, so it's negative 3i plus 8i is 5i. Next operation is multiplication. With multiplication, we begin by just using distributive property. First example, I distribute 3i. 3i times 2 multiplies to 6i. 3i times 7i multiplies to 21i squared. Now, we have to think back a few video lessons ago, we defined I squared to be negative 1. That's what got the ball rolling on all this imaginary complex number stuff. I squared is negative 1. So what we need to do, every time we see an I squared, we need to replace it with negative 1. So this is really 6i plus 21 times negative 1. That, of course, is a negative 21. I'm going to lead with that negative 21. Negative 21 plus 6i. And that's the answer we want. We don't want any I squareds in our answer, as complex numbers don't have I squareds. They have real plus imaginary. That's the form we want. So any I squareds, we have to clear them out by replacing them with negative 1. Now, FOIL problem. Binomial times a binomial. I'm going to run through all these FOIL products. 3 times 4 makes 12. 3 times negative I is negative 3i. 2i times 4 is 8i. 2i times negative I is negative 2i squared. Okay, we can combine these numbers. So we have 12 plus 5i minus 2. The I squared is a negative 1. So I'm replacing I squared with negative 1. That becomes 12 plus 5i. These become plus 2, which gives me some more like terms to add together. 12 and 2 make our 14. Okay, 14 plus 5i. Alright, here are a couple problems for you to try on your own. It'd be a good opportunity to pause the video, work them out, and then resume play when you're ready to check your work and see if you've got them right. First one is a subtraction problem, so it's just like terms. Finding my real and imaginary like terms. 4 minus 11 is negative 7. 5i minus 6i is negative I. That's done. Okay. The next one is a product. We have to FOIL the product together. So I'm going to run through these steps. We get 12 plus 18i plus 10i plus 15i squared. So the i's add together, we get 12 plus 28i. This 15i squared is really a negative 15. So we add the real numbers together, we get negative 3 plus 28i. Next, I want to show you how to evaluate powers of imaginary numbers. I will just say is I. Okay, we know that I squared is negative 1. I to the third, let's do it up here. I to the third is the same as I squared times another I. And if I squared is negative 1, negative 1 times I is negative I. I to the fourth is simply an I squared times an I squared. So it's a negative 1 times a negative 1, which is 1. Now let me do one more for you. If we were to do I to the 5th, I to the 5th is I to the 4th times I to the 4th is 1, and we just get I. So what happens is, once we cycle through these first 4 powers, I to the 5th just repeats as I again. And what we see is just a kind of a cyclic pattern of every 4 powers repeating. This would be I to the 5th, I to the 6th, I to the 7th, I to the 8th, I to the 9th, I to the 10th, 11th, 12th, etc. And the simplified forms of these powers are going to just keep repeating themselves over and over and over again. So here we're asked to simplify the powers of these complex or imaginary numbers. The first one, I to the 29th power. Now what you could do is you could take that list of every 4 powers and just count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And you just keep counting them through and see where you land. Okay? It's perfectly valid. It's going to work every time. If the power is really big, you might be counting a long time. The other thing we can do is we can take that power 29 and divide it by 4. 29, or 4 goes into 29 7 times with a remainder of 1. It's the remainder that we want. The remainder is the power that we want. So in other words, I to the 29th is the same as I to the 1st. And I to the 1st is just I. So I to the 29th simplifies to just I. Okay, next, I to the 54th power. I'm going to take 54 divided by 4. 4 goes into 5 one time. 4 goes into 14 3 times. We get a remainder of 2. So I to the 54th power is the same as I squared. And I squared is negative 1. Okay, in the last example we have 4I to the 14th power. I to the 14th power, we take 14 divided by 4, goes in 3 times, so we get a remainder of 2. So I to the 14th is the same as I squared, which is negative 1, but we have 4 times negative 1, because there was a 4 right there. So 4 times negative 1 is negative 4, and there's our answer simplified. Alright, we're going to end this section by looking at division operation. Dividing by complex numbers or dividing by the imaginary number is similar to dividing by a square root. Since we know that I is a square root, and we can't divide by square roots, that means we can't divide by i's either. So what we're going to do to simplify all these problems is we're going to rationalize the denominator. Okay. To rationalize the denominator is where we multiply top and bottom of the fraction by generally the denominator. So that's where we're going to start this one. We're going to multiply top and bottom by I over I. Okay, if we distribute in the numerator, it gives us 3I plus 10I squared. Denominator is I squared. Now the I squareds are negative 1s, so we have 3I minus 10 divided by negative 1. And then I'm going to split this fraction up to simplify. Okay. Negative 10 divided by negative 1 is positive 10. 3I divided by negative 1 is negative 3I. There's our simplified answer. In the next problem, we have 3 plus 7i divided by 8i. I'm again going to multiply top and bottom by I. I don't have to multiply by 8i because the 8 is not under a square root. Only the I is under a square root. Or only the I is a square root. So we distribute in the numerator, we get 3i plus 7i squared divided by 8i squared, which is 3i minus 7 divided by negative 8. Now, even though I can't reduce really any of these, I am going to split it up and write it to look like a complex number. So the negative 7 over negative 8 is positive 7/8 minus 3i over negative 8 is minus 3/8i. There we have it. The last example to look at is one in which we're dividing by an I, but the denominator contains two terms. We're still going to rationalize. We're going to multiply top and bottom by what we call a complex conjugate. A complex conjugate is the same two terms, the 5 and the I, but we're going to change the sign between the two terms. We're going to multiply top and bottom by 5 minus I. Okay. So what we need to do is FOIL on top. So if you want, you can draw the lines in here. We're going to run through this, 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 and this. Okay, we're going to do the same thing in the denominator, but in the numerator we get 40 minus 8i plus 10i minus 2i squared. Denominator, I'm going to do the same thing. I'm not going to draw the lines though. It's 25 minus 5i plus 5i minus I squared. Now the reason why this works is the whole purpose of rationalizing the denominator is to get rid of the I in the denominator. And you see that the like terms down here, negative 5i, positive 5i, they add to 0. It's only going to happen if we use a complex conjugate pair. If we change the sign between the two terms, will that happen? So the numerator, I get 40 plus 2i, I've added these like terms together, plus 2 divided by 25 plus 1. So we get 42 plus 2i over 26. I am going to split this up so that I can reduce the fractions. 42 and 26 both divide by 2. So we get 21/13 plus, same thing on the other one, will be 1/13 I. And that's finished.